Hi everyone, I'm really happy to be back here. I missed the last couple of years, and I can tell you from what I've seen in the talks, the level has really jumped up here. So very exciting stuff here. I hope to see more of it in the future. So I'm going to talk to you guys today about a project that we've been working with for the last 3 years that we call the Desert Fireball Array. And what this consists of is several cameras that we have around the Tucson area that stare at the sky every night looking for meteors coming in. Now we've had some other talks about this. The sky cams put up by Sandia Labs, which is where we started. But I'm going to give you an overview of our project and then where it's gone and what we're doing now and what we're doing with the data. So we're attempting with these 3 cameras to capture videos of incoming fireballs. We're doing light curve analysis from 2 directions. This also allows us to record the spectrum and the trajectory of the incoming fireball. And then one of the goals of the project is to be able to track it to the ground and go recover a piece of the meteor that we just had all the data coming through the upper atmosphere. To the best of our knowledge, there hasn't been anyone who's tracked a meteor with cameras, also had spectroscopy, and then picked it up off the ground. Once you're able to do that, then the next thing you can do is go into the laboratory and do things like burn the meteor and see if it burns in the laboratory the same way it does up in the atmosphere. And one of the reasons why this is interesting is because the area up there that you see the burn phase in is such a high vacuum that we cannot reproduce that on Earth. So the colors you see up there we actually don't get down here, even in advanced laboratories. So this is one of our brightest events. It's pretty crazy, huh? This is one of our brightest events ever. Now what was interesting about this event, it came in the middle of the night, and it was never reported or seen by anyone else that we can tell. And unfortunately our other cameras were down at the moment, so only my camera got this thing. But it would have been spectacular to watch this. Now, as you look at this thing, repeat, there's something very strange about this that we don't understand, and I'm going to point it out at the end of the talk. So take a look at that and tell me if you see something that's unusual about this. Okay? So just stick that in the back of your mind. So Sandia Labs is the people who got this thing started, and Sandia is not actually interested in the meteorites at all. What they're interested in is calibrating their spy satellites that are looking for nuclear explosions on the ground against the fireballs that are coming in from these meteors. So I think we're a little bit worried about Iran and some other places that could be causing problems for us. So that's their thing. So they don't really care what we do. They've got a lot of cameras out there, as you can see, all around the country. Canada's got their own group up here. But you can see ours down here in southern Arizona. We've got our little triplet down there. So there are quite a few of them out there. And I think eventually we're going to see stuff coming in all over the United States. So these are pictures of the original Sentinel cams. We mount them on the roof. Generally speaking, we point them at each other, but we're doing some different things now. But this is where we started, but we've since evolved. We're no longer using this style housing. We have a new housing that we've developed ourselves because this is much smaller, it's airtight, and it's much more rigid. We've also dispensed with a lot of the heaters and everything else that was in the original Sandia stuff. And we've gone just to a very simple desiccant and camera with a 100-degree field of view lens instead of the original 360-degree fisheye lenses. And the reason why we did that is because we point these cameras at each other, and the 100-degree field gives us better resolution to track this bolide through the air. So very simple. You can build one yourself, and this housing is electronics housing, and it's completely airtight. So this is the way it sits in southern Arizona. Those are our 3 cameras. They're about on a 60-mile baseline looking at each other. So we have an intersection area that involves, a couple of hundred probably square miles. And in the bigger picture, though, we can look out almost 300 miles from each camera. So we're looking over each other's shoulders. So we have about a 300-degree total field of view to catch stuff in. Now, outside of our mutual area, the mutual detection area, we'll only get 1 camera on it, but we have some other methods that hopefully will help us triangulate the position of something coming in. So this is what the information looks like. Now, we're no longer using the Sentinel program. The Sentinel program had a lot of problems. You have to mask out the street lights. If you have blinking stars that get near the horizon, they start triggering this thing. And it would not be common to, it was common to come in the morning and have 50 or 100 false triggers filling up your computer, which was a big problem. We tried many ways to get rid of it. But now we found this UFO capture software. And even though the title of the software sounds kind of crazy, the software is really excellent. It's made by these 2 guys in Japan, and they use it for capturing sprites and a bunch of other things as well as meteors. And what they do here is the dark blue dots that you see here are automatically generated on every light spot that is in the field. So most of these blue dots are stars that are covering up, and the mask moves because it's being generated on the fly. It moves as the stars set. This has made a tremendous difference, tremendous. I think we get maybe one false trigger a night. Many nights we have 0 false triggers. And it's also increased our sensitivity because it's just looking for things that are changing against a basically black background as far as the software is concerned. When we do get a detection, it stacks them all up and shows us the entire run of the meteor through the atmosphere. So we flip through our exposures in the morning, and if we see a big one like this, we go, oh yeah, and then the emails fly, we say, did you get it, did you get it? So very interesting. But there's a couple other tricks that have come up recently. The Fry brothers have recently published a paper on using NEXRAD weather radar to detect bolides coming through the atmosphere. Now, they actually archive these radar passes, and they're done at various elevations and at various frequencies with various noise features. There's a whole lot to it. But what we can do is we can go back and look in the radar data to see if we can see the bolide. Now, we're not actually trying to detect the bolide coming through the atmosphere, but when it does come in through the atmosphere, you know, it releases a lot of crap on the way through, and this stuff rains down over the next few minutes, and that's what the weather radar can see. Now, one of the more famous situations where this did work very well was in Wisconsin, where one came in, I think it was about 1.5 years ago or 2 years ago. They found the location based on weather radar, and it produced a line across the weather radar. So you can do this at home. This is one of these at-home things, so maybe that one in California somebody could have seen on the radar. So another thing that we're using, we have to synchronize all 3 of these clocks, and you've heard this time sync thing from a couple of other talks here today. Well, we highly recommend this Mindberg NTP software. We've found this software to be different from every other clock syncing software we've ever seen because it actually adjusts the frequency of the oscillator in the computer to keep your clock on track. So I don't know of any other piece of software that does that. So it uses the standard, internet time references, but then it'll adjust the frequency to keep you on track. It's very common for us to have the bolide start and stop on the same frame. So we don't know exactly how accurate it is, but it's milliseconds, and it's well within the threshold of what we're looking for. So good recommendation there. We're also trying to get spectroscopy of the meteors. There have been some spectroscopy done on a lot of the showers, but not so much on sporadics. This has been one of the harder things to do because they're fast and they're not actually that bright. ST7 here, just a simple lens, and behind the lens there's a rainbow grating, and it produces a low-resolution spectrum. And here's one you can see. Upper right-hand corner is the bolide, and very faintly to the left is the spectra. We come in here in reverse image, you can see it a little better. And then once we put a line through it, you can see you can actually capture a spectra. This is the area where they're most behind on, though. This is turning out to be pretty tricky to do. So we're still working on this, but it's part of the equation because the burn's what's telling you what elements are going on, et cetera, et cetera. So once we get the thing, we're actually capable of laser ablating it. This is my laser ablation station down in my lab in my basement. We can create a plasma fireball and see what it's doing, and then compare it to the spectra that we got up in the atmosphere. So this is a mutual detection from 2 cameras, one Sierra Vista and the other one in Tucson, who in this case happen to be using a 360-degree lens. So once we get the 2 detections, a mutual detection, we can put it through a bunch of math, and we come out with a lot of data. So we can get the light curve, we can get the position, we can get the distance, all this stuff. And I can show you a bunch of graphs, but you know if a picture is worth 1,000 words, a 3-dimensional picture is like worth an encyclopedia. So this was a problem because we wanted to know where potentially these meteors were landing, and we wanted to do it fast because we wanted to get out there and find it before anybody else did. The last time a meteor came in next to my town, within 48 hours they had found it out in the whetstone. So there's a lot of meteor hunters out there. So what we decided to do was use the best 3D program we know of, which is Google Earth. And our first attempt here was to recreate the bolide trajectory in Google Earth. And in this case, this is Santa Fe detected this one. It's over Mexico. And then my place in Sierra Vista detected it. And this was a 350-mile distance from Santa Fe to this meteor. So you can imagine the range we can get on this. So that was our first attempt. But now I'll show you where we're at here, and hopefully we're going to see a video go here. trying to look at this video so you can get an idea of the three-dimensionality of these trajectories. And you see a couple of different ones. We have some straight ones, which are the ones we do fast and quick just to see where it potentially landed. And then we have others that take each frame of the video and position it in 3D space. So that's our three-dimensional part of it. Now we can look at one of these individually. So this is a very short, fast, bright meteor that came in. We'll take a close look here. And the red line, obviously, is the trajectory. But you see this white fuzzy stuff on the top. What we've done there is we've superimposed the light curve on top of the trajectory. So by looking at this one image, you can get a feel for what this thing was doing when it was entering. So in this case, it just got brighter. It got very bright, then it burned out quickly. So that's fairly typical. But what we're demonstrating here is the ability to combine more than one data set into the three-dimensional picture. There's another thing we can do with this, though. This is like a gunshot. Think of it like a bullet. So if we look down the barrel of the gun, which is what's happening here, that little red dot now is that line. We're looking down the barrel of the gun. This position down on the ground, just over into Mexico, is the furthest distance that that thing could have landed. So that is the top of the search ellipse that we would have. The next thing we do is we look straight down from the end of the burn phase, and that's the closest that the ellipse, search ellipse could be. And that would be just inside the border, so we never go to the border anymore. But you get the picture of how we would say, okay, this thing must have landed in an area this big. And our error bars are about plus or minus half a mile wide. So our ground track on this thing is about half a mile either way. So we have a fairly narrow area to go look for. So it makes it very reasonable to assume that if we get one that lands on the ground, that's the question, how many of them actually land on the ground, we could go out there and find it. So here's another one. This is the longest one we ever had. Now this one goes for 9 seconds and actually goes off my frame. Tucson got it going away from them. And it'll play again here. This thing was so slow that we thought, well, maybe this is the reentry of a piece of space junk. Turned out not to be. Once we analyze this thing, you can see the number stats on this. So forgive me for not using the more conventional metric stuff, but I think people in this country get a better feel for miles an hour in this particular application. So 25,000 miles per hour entry speed, started burning about 50 miles up, quit about 25 miles up. It went 50 miles horizontal and 25 miles down just in about 9 seconds. So again, if we take a close look at this, there's the light curve. Now if we superimpose the light curve onto the trajectory, you can see what it was doing. Very slow burn. Interesting thing about this meteor, if it didn't have that north-south component to the trajectory, it may have soft landed onto the Earth, because this thing was almost exactly matching the Earth's orbit through space as it was coming in. So I'd like to catch one with a catcher's mitt.
You got to be the size of a house.
Yeah. So yeah, very interesting, that possibility. So here we are now back to this one that we showed you in the beginning. Now there's some very interesting unexplained things in meteors. How am I doing on time?
6 minutes.
Oh, 6 minutes, I'm ahead of the game. Total, okay. So there's interesting things that happen. One of the things that they've discovered lately that is a questionable thing, talking about these millisecond time flashes in stars, if they think they've detected millisecond time flashes in meteor reentries. Now the problem is nothing burns that quick. So there's a question as to what can cause a millisecond flash like that, or a few millisecond flash. So that's an undiscovered or unknown phenomena that they think they've seen in meteors that we would love to try and explore. So I was listening to those other talks with some interest. So as we look at this thing come in, it explodes, bang, and then right here, debris comes out the other end, and it's still burning. Now what we don't understand about this particular reentry is that something else is burning up here in the explosion. And note that they both burn for about the same length of time, both the initial explosion and the debris coming out the end. Now, what's interesting about the explosion up here is that it stays in place. It doesn't move. And we even centroid it with Maxim. We went through each frame to see if it moved at all. It didn't move at all. So we have no idea what could burn for that long and have zero momentum, zero mass. That thing's coming in at thousands of miles an hour, as you know. What stopped and then sat there and burned in the upper atmosphere for that long? We would really have liked to have had a spectra on this, because maybe it would have told us something. But this is one of the interesting mysteries that we would like to explore in this area of meteor reentry. So come see me if you've got an idea. So future plans, we want to expand the network. If anyone in our neighborhood wants to get involved, let us know. We're also would like to add radio detection. Thomas Ashcraft up in Santa Fe, New Mexico, has been running a radio detection stuff very successfully up there, and he publishes stuff on his website. Infrasound is one of the big deals that we would like to install also, because when they come into the lower atmosphere and make a sonic boom, it can be detected many, many miles away through the infrasound signatures. And there have been papers published on this where infrasound things have been used to analyze the incoming meteor. Also, we want to automate the data reduction, which is one of my requests, as everybody's had since this talk. If anybody wants to work on these KMZ files in Google Earth, we put them together manually now. We'd like to be able to pipeline that. So if you're that kind of guy and like to do something like that, let us know. And the last thing that I hope to come back here and tell you next time is that we found a meteor and we're ready to start analyzing it. So that's my talk. Thank you.